Well, welcome back to the home laboratory. What we're going to do today is we're going to build a lightsaber using the aptly named Slayer circuit. So I've been playing around with a few circuits recently, and as you know I keep them in these little boxes, and here's an idea I got from eBay. It said mini Tesla coil. For those of you who know what a Tesla coil is, it's not quite a Tesla coil in fact, but it's very similar. It's a high frequency transformer that turns low voltages to extremely high voltages, and it works in a very similar way to a Tesla coil. And this circuit is called the Slayer circuit, and we're going to use this to build our lightsaber. So let's have a quick look at our circuit, and you can buy the parts for this and put it together. It didn't take me very long, though go easy because there are some very high voltages here. So I'm going to very quickly talk about the Slayer circuit. It's a wonderfully clever and very simple circuit, but it's in fact rather difficult to explain, and I might save that for another video. But let's just have a quick idea of how it works. So it's strangely DC in, which is strange for a transformer circuit. It has about 2 turns on the primary of the transformer and hundreds of turns on the secondary. So you can understand that this is a step-up transformer. So we're going to get very high voltages on the secondary. But transformers need a changing current to work. So DC is not going to help. So very quickly and simply, switch it on, and a transistor in this circuit switches on, okay, becomes positive, shall we say, and allows current to flow through the primary. That current rushing into the primary induces an EMF on the secondary turns, and it's a little bit more complicated than that because there is a capacitance between the secondary turns and the ground. It has its sort of own capacitance. We don't put a capacitor in there. That has the effect of creating an EMF on the secondary, but in such a way that one of the terminals of the secondary that feeds back to the transistor becomes negative and therefore switches off the transistor. It then gets a little bit more complicated. The magnetic field then collapses and has the effect of turning the transistor on. And suffice it to say, and I don't really like these very simple explanations, but suffice to say, what happens is the circuit is set up so the transistor feeding current into the primary is turned on, then turned off, then turned on, then turned off. This is a self-oscillating circuit. And if it oscillates itself, controlled by the components in it, and particularly the inductance of the secondary turns and the capacitance to the ground, then we've got an AC system. So in summary, the Slayer circuit takes a DC voltage, feeds it into a circuit that resonates with AC, and that creates the AC we need to create changing magnetic fields that can then cause this huge step-up transformer to work and create very, very large AC voltage pulses on the secondary. So let's wire it up and see what it does. Okay, so let's connect up our little Slayer circuit to the lab power supply. It needs quite a bit of current, this one. So there's the plus and the minus already connected. And I'll turn on my power supply. Some of you might remember I have this little flashing light here just to remind me that the power supply output is on. It's a good idea to have something like that because with this power supply you can actually dial up a voltage, switch off, and then switch back on, and that voltage is suddenly there, and you can blow up components if you've forgotten you haven't got it set to 0. So this one works from about 15 to 24 volts DC. So what we'll do is we've got the output voltage on, so I'm going to turn up the voltage and we're going to get to about 20 to 24 volts, and you'll see in a minute we've got a couple of LEDs that turn on the back of the circuit, and I'll show you how we can get our lightsaber to work. So what are we going to use as our lightsaber? Well, I'm going to use one of these fluorescent tubes. You might remember that these are often mounted in the light sockets in the roofs of buildings, or we've got these type of bulbs which are going out now, the compact fluorescent tubes. But what's interesting about them is there is no connection from one end to the other. There's no metallic filament between the two ends like a regular Edison type light bulb. What's in here is mercury vapor, and inside the glass is a fluorescent coating. That's the white you can see. So we're going to use this as our lightsaber, but we're not going to connect it at all to a source of power directly, and I'm going to have to explain how does it manage to work. Okay, so let's turn on our little Slayer circuit. There we go, and bring our lightsaber up. And there we go, it lights. Take it away, it's off. Back in again, and it lights up. So we're lighting a light bulb in our hand without any direct electrical connection. So you all know me well enough now to know I wouldn't cheat, but I guess for those who might be new to this channel and think I'm hiding something in my hands or wires, so I'll just pick up the tube like this, and there we go. So there are really no external electrical connections at all. It's the field created by the Slayer circuit and the secondary coil that lights up this fluorescent tube. So no FJ's physics would be complete without a little bit of a physics explanation. You'll notice the light bulb lights really well if I hold it this way, and not quite so well if I hold it there, like that. There's a good reason for this. The field varies away from the Tesla coil, or at least from the Slayer circuit coil, and it gets weaker and weaker and weaker. So we've got an electric field gradient along the tube, and that is needed to ionize the gas in the tube. When I put it like this, there isn't such a gradient between here and here, so it doesn't really light as well. So I'll quickly explain why that gradient causes the tube to light up. So one of the reasons these tubes are being phased out now is that they contain mercury vapour, and mercury vapour is quite toxic. As you move away from the coil, the field varies in strength. That's a field gradient, and this is what causes ionisation in the mercury vapour in the tube. So if you put the tube sideways, there isn't much of a variation in field strength. You're parallel to an equipotential, so there isn't enough potential difference across the tube to cause ionisation in the mercury vapour. It's the change in field strength along the tube that causes the mercury vapour to ionise, and then it's those ions and electrons that recombine, giving off photons of invisible ultraviolet light that hits the white phosphor on the inside of the glass tube's surface, causing it to glow and give off the light that you see when the lamp is on. So to end with, I thought you might like a little bit of a story, and this is really quite fun. It's told to me by a friend of mine many years ago, Gary, who I've completely lost touch with. I have no idea where he is, but he used to work as an RAF engineer, and he worked on the Vulcan bombers. And he tells this wonderful story. I'm not sure how safe this is, but I'm going to tell it you anyway. He tells me this wonderful story of the Vulcans in the hangar, and the hangar was lit up with fluorescent tubes in the roof. And these tubes used to fail from time to time, as they do in the home. So they call in the engineers and say to the engineers, "Can you change a few of those lamps, please?" I guess they changed them all because it was such a tricky job, probably going up to a great height on a cherry picker to replace the tubes. Anyway, what they didn't tell the engineers who were changing the light bulbs was, and this is the bit I think is a bit dangerous, that they turned the radar on, that's the radar transmitting system, on the Vulcan. Now, I don't know how you do that or how it was done, but that's how the story goes. And rather like our little Slayer circuit, that produced a strong enough field for the light bulbs to light up. So what they did was they waited until the guys had got the tubes like I have here in the cardboard packages, and then as they pulled them out of the cardboard package, they lit up. And the engineers were truly amazed. And the guys on the aircraft, Gary and his friend, said, "Oh yeah, we ordered those especially. They're top secret. We only use them with the Vulcan fleet and in the Vulcan hangars, and they're self-lighting light bulbs. And what you want to do, guys, is put them back in the packet, and when you put them back in the package, they switch off. So when you put them in the roof, be really careful, because these self-lighting light bulbs are really, really expensive." Well, I've no idea of the risk of doing such a thing in a hangar, but I think they had the guys fitting the light bulbs fooled, and they must have gone home and said, "Gosh, we've seen the most incredible thing today. Light bulbs that light up without even being connected to a power source." So, I hope you enjoyed that brief look at the Slayer circuit and our homemade lightsaber. I'll be making another video soon, so I look forward to seeing you then.